right, so let's talk a little bit about polar bonds, polar covalent bonds specifically. It's a really important topic in organic chemistry. A lot of the reactions and understanding tends to come out of polar bonds. They also tend to be the molecules that do the most chemistry, or the ones that are polar in the first place. Right, so just a simple example to start. Carbon, oxygen. This is a polar bond. If we imagine, again, not really a full molecule, just kind of thinking about it as a bond, right? A covalent bond means you've got this cloud of electrons around it that are shared, right? So most of the electrons are shared in between carbon and oxygen. And if we're thinking about the electron sharing, we're going to think a little bit about electronegativity as well. Think back to what we've done before. So electrons are shared between our atoms, but they aren't necessarily shared evenly, right? So we've got a cloud of electrons. Let's label it just so we're clear, right? But within that cloud of electrons, oxygen is the more electronegative atom. Use a big capital EN just to abbreviate electronegativity, for clarity's sake there, right? And what was our definition of electronegativity again? So that was an atom that had a strong affinity for electrons, that pulled the electrons in closer to its nucleus. There's another video just for electronegativity, which is almost even more important than this one. And if that happens though, it's not only just going to pull its normal electrons, now that it's sharing some of its electrons, it's going to pull this whole system over that way, right? So what you'll end up with is a whole bunch of electrons, relatively speaking, over by the oxygen compared to less so on the carbon, right? So you end up getting a pole, right, like a plus minus, like a magnet, where you have more of a negative charge on this oxygen, and thus, since all the electrons have been kind of pulled away from carbon, you end up with a more positive charge on carbon, right? So this is, two different atoms. One's more electronegative. It's kind of going to drag all these electrons, kind of pull them, suck them in towards itself, right? And a less electronegative atom is going to lose out as a result of that. So you get a negative side and a positive side. That's a polar bond, right? And so I use these symbols to represent partial charges, right? So instead of a full ionic negative charge, an oxygen bonded to a carbon is just going to have a partial negative charge. Thus, the carbon itself is going to have a partial positive, and that's one way to kind of represent that on a molecule, on any structure, to show that there's a polar bond there as well. Okay, well, this is going to be more positive, that's going to be more negative. The traditional way of doing that also is the dipole arrow following along that bonds, and that means the same thing essentially, right? So this plus end conveniently next to this carbon, that's the positive side, and the arrow is the negative side. And also it's kind of showing the direction that the electrons are being pulled there in that polar covalent bond. The electrons are being pulled up towards the oxygen. Again, just another way of showing it. And all right, so we can keep track, we can figure out if something's negative or positive based on, all right, let's look at any two atoms and kind of connect them together. Which one's more electronegative? Any two atoms, if it has an electronegativity difference, you're going to see a polar bond. Some are really, really weak, so that they're almost not really considered much of a polar bond, like carbon-hydrogen. There is technically an electronegativity difference between those two, but mostly we're kind of considering that to be nonpolar just because it's so negligible. Carbon-carbon, right, that's going to be completely nonpolar. I do have a pi bond there. Doesn't make much of a difference for polarity. The dipole's still going to be the same, whether that was a single or a double bond there. Some keys and useful bits of information, though, is where can we use this, right? Rather than just, all right, that's a dipole, that's not a dipole, that's a dipole. That's not super useful. But we do a lot of chemistry, and you probably do reactions of this kind of functional group, and you can think about it, all right, carbon positive charge, right? That's a potential electrophile, right? Something that's going to accept extra electrons and maybe start a part of a reaction. And thus also this oxygen, right? I haven't drawn it because they weren't really involved in the dipole. It's got lone pairs, it's got a partial negative charge, right? This is a potential nucleophile. Right? So what we want to do, really, if we can get good at organic chemistry, it's not, I remember that this functional group does this and this, or this one reacts with this one, is, all right, here's a functional group, what's it going to do, right? It has a dipole, right? It's got lone pairs up here. You know, maybe this can act as a nucleophile. Maybe this can react with a nucleophile, right? A potential electrophile here means that something more negative, it's not going to interact up here, it's going to go down there, right? And that's the predictability that it's useful in organic chemistry. And so dipoles, of course, relate also to intermolecular forces, but in terms of chemistry, you know, this is a really important concept. All the functional groups you'll look at, they're all going to have these sort of concerns. Is it polar? You know, does that dictate where new reactions go?